Well, hi everybody. Hello, good afternoon, and welcome to the Big History class. It's a real pleasure to see you all. I'm Walter Alvarez, and I think I've been in email contact with most of you over the last couple of months. And so it's really nice to see you in person. It's been fun being in email contact, but this will be even better, I think. So welcome to the Big History course. And I want to start by introducing some people, but we're not going to spend very much time on logistics today. Tomorrow afternoon at 5 o'clock in this room, everybody who's registered or who is on the wait list and hopes to be in the class should come to that, and that's when we'll go over the logistics. But today I got such a neat story to tell you that I don't want to waste a lot of time on logistics. But let me start by making some introductions. So anyhow, I'm that first person. We have two graduate student instructors for the course, and they're in the back. Ryan Kelly, hold up your hand. Ryan's the head GSI. He did this last year. And Ryan is a biologist and has a PhD in biology and is now a law student where he's learning about environmental law. I think you'll find Ryan really an interesting person to talk to. And we're glad to have a new GSI who's David Mangiante, who is in our department, and it's really good to have him joining us. And there are two other people I want to introduce. First, I left out, how did I leave out Roland? Just a minute. Okay, here. Okay, so Roland Sakow is back there behind the video camera. Hold up your hand. Roland took this course 2 years ago as a senior, and as his project, he came up with the most amazing way of visualizing all of time. It's something called chronozoom, which some of you may have seen, and we're going to use it very intensively in this course. And Roland works for me now developing chronozoom, and he's going to be helping with the class. Everything technical will run much better because of having Roland here. And then I also wanted to introduce in the back corner, that's David Shimabukuro. And David is a graduate student with me just finishing his PhD. And a few years ago, David and I started this course together. So he was the founding GSI, and so a lot of what we're doing will reflect input that David made into this course. And frequently, when you come to my office for office hours, which is upstairs in the next floor over in that corner, you'll run into David because he's around there, and he's a really good person to ask big history questions to. So he has other things to do, but thanks for coming by, David. Okay? So the only thing we're doing right now in the way of business is I'm passing around this sign-up sheet, and would you please sign up on here? It has all the people who are either enrolled or on the wait list. If you're not one of those people and you're still hoping by some miracle to get in, maybe put your name at the bottom or something with your email. But you guys haven't done it yet, so do that, and then we'll pass it around and we'll make sure that you've signed this by the time you leave. Okay? All right. We've been doing logistics by email for so long that I want to start out with some big history and show you why I find this topic so enormously exciting. I think that you will find as we go through the course that we learn about different aspects of big history. We will learn, for example, what happened when, the standard view of what history is. We won't do that in any great depth because obviously you can't do that for all of time in one semester. Somebody calculated how many 100 million years a minute we would have to be going through to do that. So you will get a broad outline of what happened when in the history of cosmos, of Earth, of life, and humanity. But we will also be doing another thing, which is to think about what it all means and what are the connections. For example, when the Earth came into existence, which was about 2/3 of the way from the beginning of the universe to now, what changed? What was different when you got a solid planet with liquid water on it? What was different? And then what was different when life appeared? So we'll be thinking about the significance or the understanding of history that comes like that. But today what I'd like to do is to start out with a case study. And we'll have a few of these as we go through, basically chances to see how these different kinds of history, the history of cosmos, the history of Earth, the history of life, and the history of humanity, how they interact in particular cases, in particular case studies. So that's what I want to do with you right now. I hope that you're going to find this story as interesting as I do. And let me encourage you right from the beginning, don't hold back. Hold up your hand and ask questions. I think I said someplace that nobody in my class ever regrets asking a question because it will always lead to something interesting. So please do that as we go. It will make the class much more lively and much more fun for everybody. So, are you ready to go?
Yes, sir.
Okay, here we go. We're going to talk about oceans of bronze, and if you don't know what that means, well, that's part of getting you excited and interesting. So we're going to start by talking about a time which was part of human history, which was the Bronze Age, and in particular, we're going to talk about the end of the Bronze Age. Oh, great! David's brought in another chair. Thank you. Come in. Those of you who've just come in. If you've just come in, don't forget to sign the sign-up list when it comes around. Okay, so we're going to talk about the Bronze Age, and particularly the end of the Bronze Age, which turned out to be an interesting time in the sense of what I've been told is a Chinese proverb, or curse maybe, may you live in interesting times. So the people at the end of the Bronze Age lived in interesting times. Now, I think almost everybody has some idea of ancient Greece. And the ancient Greece that we usually think of is what we might call classical Greece, say around 400 BC, maybe from 500 to 300 BC, something like that. This is the Parthenon, the great building in Athens that represents that time. So this is probably the mental image that comes to your mind when you think of ancient Greece. Is there anything else that comes to your mind when you think of ancient Greece?
Hercules.
Hercules, okay. And what about a poet? Homer, of course. Okay, so at least in my mind, before I started to get deeply interested in this, I think that the Parthenon and Homer were somehow mixed up together, and they shouldn't be because they were a long time apart. So Homer, and I hope you can see what's at the bottom. I remembered. I'm going to shift the captions up to the top so that you can see them better. At the bottom, it says Homer was around 800 BC, so he was 400 years before the Parthenon, and he was writing about the Trojan War, which took place around 1200 BC, which is 400 years earlier than that. So there's an 800-year range there of these things that we commonly mix up in our minds. And I want now to talk to you about Homer's story of the Trojan War, or at least I'm going to use this as a way to start. It says here, you may not be able to see at the bottom, it says, behind a great legendary story like the Trojan War lies an intricate and fascinating texture of cosmic history, earth history, life history, and human history. Most people, when they start reading Homer or thinking about Homer or the Trojan War or the Odyssey, they don't realize that this has ties into what happened in the history of the earth or the history of life. And that's what I want to show you today, how all of that works. That's why this is a case study. So Homer's legend of the Trojan War is set in the Bronze Age, and I want to look with you at the chronology and see what lies behind the legend. If you're in the back and you can't see, at the bottom it has a little timeline there. It shows 3 major times in the history of human development, from the Stone Age, when stone tools were used, to the Bronze Age, when bronze being the first really useful metal that humans learned how to use, and then finally to the Iron Age that we live in at the present time. And these are maybe not the most important things that happened in human history, because there were developments in government and law and religion and all sorts of other things. These are commonly used because these are the things that archaeologists can find in excavations. I mean, an archaeologist is not going to find something that tells about what the laws were a long, long time ago, not very often. But all the time you find stone tools or bronze tools or iron tools. So this is useful to one kind of people, archaeologists, who study human history. So the Homer's legend is set in the Bronze Age, this sort of middle episode in technological history. So let's look a little bit at how this lays out on a timeline. And if you'll see at the top, older is on the left, younger is on the right, and that is going to be almost always in this class. That's going to be our convention, is that old is at the left and young is at the right. When you get to seeing chronozoom next week, you'll see that it's always laid out with old on the left. So what you can see here, and I guess I forgot to bring a laser pointer, so I may be walking around here a good bit. Any rate, so anyway, this is the time in Greece that we usually think of as ancient Greece, with Socrates, Plato, Aristotle, Alexander the Great. After Alexander the Great, Greek culture spread all over Western Asia as far as India, and that's called Hellenistic Greece. Before that was something called Archaic Greece. And before that even was Dark Age Greece. And Dark Age, as you might expect from the name, we really know very little about. And what happened before that? In Greece itself, it's pretty hard to say. There's some evidence. But if we want to find out what happened before Dark Age Greece, a good place to go is the island of Cyprus. Did any of you have a chance to look at Cyprus on the clickable map that I sent you? Roland made that clickable map when he was first a student in this course. So those of you who've had a chance to do that know a little bit about this island. And it has quite a good record of what happened before the Dark Age, in early Bronze Age Cyprus and Middle Bronze Age and Late Bronze Age, and there's some dates on there. And so why was there a Dark Age? Now, a Dark Age is something that we don't know anything about, and this is a major feature of ancient history from the Eastern Mediterranean. And it's sort of part of our question today. It seems that about 1200 BC, and that by, if you like to know dates, that's a good date to know, about 1200 BC was something that's been called the catastrophe of 1200 BC. It was the end of the Bronze Age. It was maybe not the end of all use of bronze, but it was the end of Bronze Age civilization. And we're going to see how important Bronze Age civilization was and speculate a little bit about why it came to an end. But while we do that, I'll pass this one the other way. I don't know if any of you, maybe some of you have not held bronze in your hand. It's an amazing metal. It's an alloy of copper and tin, and this is a replica of a statue made by Etruscans in Italy in the time before Rome. But just pass this around. Let me get it back when you're done, and it will give you a feeling for what bronze is like. It develops this beautiful sort of a greenish patina on it, so sculptors love to use it. At any rate, there was a catastrophe that brought to an end an amazing civilization, and it brought it to such a complete, abrupt end that 400 years of Dark Ages succeeded that. And after those Dark Ages were over, nobody even remembered anything about Bronze Age civilization. It was the utter extinction of a whole civilization. So, in the late Bronze Age, there were civilizations centered on palaces, great palaces at places like Mycenae in Greece. And they disappeared, and they were just so completely forgotten that in 1800, let's say, nobody had any idea that they were there. 200 years ago, nobody had any idea they were there. And archaeologists have uncovered them now, so we know about the Bronze Age civilizations. But that must have been some catastrophe not only to wipe out the civilization, but to eliminate every memory of it, or almost every memory, because Homer was recounting legends that were all that had lasted. What caused the great catastrophe? That's our question. Okay. But let me show you, first of all, just how devastating this was. So here is Cyprus, the island of Cyprus, and archaeologists have found quite a number of sites there. So here is one called Paleokastro in western Cyprus, and that city was burned about 1200 BC and never reoccupied. Burned, abandoned, silted over, and forgotten. Here's one. I won't even try to pronounce that. But this is a city that was abandoned in 1200 BC. It wasn't burned, but people just left and they never came back. And it was covered over and forgotten. Kition, burned about 1200 BC and abandoned. Sinda, burned about 1200 BC. Here's another one with an impronounceable name that was abandoned in 1200 BC. And there's a hint here that something bad, oh thanks Dave, something bad was about to happen, because the archaeologists have found the workshops, they've uncovered the remains of the workshops of the goldsmith, the silversmith, and the bronzesmith, and they found that these guys had taken their supplies of these valuable metals and they had buried them out in the courtyard someplace, like trying to get them out of sight, hoping they would come back and be able to pick them up and use them. They never came back because they stayed there. Something bad. Here's another one, burned about 1200 BC. And this is not just Cyprus. This is all over Greece. It's all over Turkey. It's over much of the Middle East. And something bad happened. Okay, so what might have caused this? Well, there are a number of suggestions that have been made: drought, migrations, ironworking. These last two, earthquakes and changes in warfare, those are the ones that I want to just briefly mention to you, because those look like the two suggestions that are most interesting and you know, are attracting the most attention and support at the present time. So as far as earthquakes are concerned, there is a professor of geophysics at Stanford named Amos Noor, and Amos has attributed the catastrophe to a time of intense earthquake activity throughout the Middle East. He thinks that he has evidence that there were lots of big earthquakes all at about the same time, and as a result the whole area just became uninhabitable. Now, I'm a geologist, so I probably ought to like this explanation best because it has to do with earth processes. But I have to confess that I really I'm more persuaded by the other hypothesis, which is due to Robert Drews, who's a historian who wrote a book called The End of the Bronze Age: Changes in Warfare and the Catastrophe of about 1200 BC. So what he's talking about, changes in warfare, he's talking about chariot warfare. You've all heard of chariots, chariots of fire, chariots of the gods, things like that. So chariots were the way that people used horses in warfare before the invention of the saddle and the stirrups. Imagine that you were a medieval knight, you know, doing that thing where you have a lance here and some other guy's coming at you full speed. If you don't have stirrups, you're in bad trouble. You know, one little knock and you're off, right? So in this Bronze Age time, people did not fight on horseback because they couldn't stay on the horse. So what they had was they would hook up two horses to a chariot, and the chariot would have one guy driving and the other guy would be an archer. And so there would be these great arrays of chariots that would that would go into battle against one another. And what Drews thinks is, that various people who were not civilized, barbarians at the time, learned how to defeat these chariots and sort of left the Bronze Age cities defenseless. So here are pictures of what this was like. Here's chariots with a driver and then an archer here. And here's one, this is from an Egyptian carving. Here's the pharaoh drawn big, of course. Here's his horses, his chariot, and he's up there with an arrow. So these were mobile firing platforms, and they were the way horses were used in warfare. So what Drews suggests is that the barbarians learned that they didn't have to be too afraid of these guys. You know, if you had a bunch of guys just running around on foot with a knife, they could go around, you know, they could, you know, disable the horse, and then the chariot's done for. And so his suggestion then is that Bronze Age civilizations were dependent upon chariots for their defense. When the barbarians figured out how to defeat chariots, they were able just to destroy the armies that defended the cities, go in and destroy the cities, and for some reason they didn't like cities, so they just burned them and left, and this happened time and time and time and time. You know, dozens and dozens of great cities in Turkey and the Aegean and the Middle East succumbed to this. That's his suggestion. So and it was so effective that there followed this 400-year dark age that was so deep that these Bronze Age civilizations were utterly forgotten. And then Homer now is writing maybe around 800, something like that, 400 years later, and the only thing that's left to recall these civilizations is legends that have come down through time by voice, which then Homer incorporated into his great poems. Okay, so maybe the destruction of Troy then was part of the catastrophe of about 1200 BC. So this is my prologue. And now what I'd like to do with you is to see how it ties into the different subdivisions of big history. How does this tie into Earth history, into life history, and cosmic history? So that's where we're going. Any questions at this point? Question? Boy, it must have been really clear. Okay. All right. So there are going to be 2 or 3 breathtaking discontinuities in this lecture that are going to leave you gasping. And suddenly we are out of Cyprus and the Bronze Age, and we're into seafloor spreading, which is geology. And you'll see how these things all tie together. But let me have my fun of putting these discontinuities in here. So let me tell you a little bit about continental drift and seafloor spreading, and you'll see why it ties together later. So this man is Alfred Wegener. He was a German meteorologist. He studied weather in around the turn of the previous century, and he was the first guy to propose and seriously document continental drift, the idea that if this is Africa and this is North America, they used to be next to each other and they've spread apart like that. Seafloor spreading is our modern, or actually plate tectonics is our modern theory that began with Alfred Wegener and continental drift. He spent a lot of time on Greenland, and in fact that's where he died in a failed rescue attempt. This is in his hut on Greenland. But here was his idea, and this is a little hard to see, so I've got it labeled. This is his concept of Pangea. Pangea means all the lands. Pan for all, and Gea for lands or earth. And so he suggested that the continents were not always spread out on the earth like they are now. At one time, they were all close together, and then they have drifted apart. That's continental drift. So here's what he has. Here's North America and South America on the west. This is his reconstruction of Pangea. Here's Europe and Africa, Australia and Antarctica, India and Asia. So he has them all put together into one big continent, which then broke up. And we now know that this is essentially right. You know, some of the detail, he didn't have all the details right, but his general idea was exactly right. So that means that in between North America and Africa, say right there, that used to be a continuous continent. Now it is an ocean, and that ocean has formed gradually over the last almost 200 million years by the 2 continents drifting apart, forming new ocean crust in between them. That's called seafloor spreading. And if you'd like just a first glimpse at the time scales that we're going to deal with in big history, that took a long time, 200 million years. Here's how to get a first sense of 200 million years. Look at your fingernail for a second. Your fingernail grows at maybe 1 or 2 centimeters a year. That's the rate at which Africa and Europe are spreading apart. Same rate your fingernail grows. And they have had time to grow so far apart that now it takes overnight in a jet aircraft to fly from one to the other. That's what you can do in 200 million years. First time scale introduction. At any rate, so new ocean has formed in between those two continents as they spread. I should say new ocean crust. And the man who figured out how seafloor, he first proposed seafloor spreading and suggested that that's how the continents drift, was a man named Harry Hess, who was a naval officer in the Second World War, and then he was my thesis advisor at Princeton. And he came up with this idea in the 1960s, and it was considered not only wrong but ludicrous at the time. But just like Wegener, he was right. He was scorned and disparaged. He turned out to be right. So he proposed seafloor spreading. And here was a famous drawing that he made in his first paper. This goes way, way back now. But he's suggesting that the mantle here, the deep mantle of the Earth, rises, comes up to the surface. This is very slowly. This is happening at 1 or 2 centimeters a year. It gets up there, it turns and it spreads like that. And maybe this is the surface of the ocean he didn't put in, but this is ocean crust here. And he suggested that ocean crust was made of serpentine. Now, most of you are Californians. You probably know that pale bluish green shiny rock that you see. That's serpentine. And serpentine is formed when the deep rocks of the mantle come near the surface and they get in contact with the seawater, and the seawater alters the deep mantle rock to this serpentine or serpentinite. And so Hess proposed that this was what was going on. He was absolutely right about the seafloor spreading, but he wasn't maybe right, or at least not entirely right, with the idea that what happens is that at the center, the mantle rock gets wet and turns into serpentine. Makes sense, doesn't it? There's all that seawater above it, and rock is hot coming up. It reacts easily. There's chemical reactions. You'd think it would be right. What Hess didn't understand at the time, nobody understood, was that what happens is as this mantle rock rises, it's hot down here, as it rises, there's less and less pressure on it. And it undergoes what's called pressure release melting, which means that this hot rock is no longer, doesn't have a big weight on top of it any longer that's keeping it solid. As it gets near the surface, it melts. And so melting takes place. It's not just getting the rock wet, it actually melts. And something new happens, something different forms there. So this was Hess's idea, rising mantle, seafloor spreading there, and then the mantle getting converted into serpentine. Just to be completely honest about this does happen in some cases. But in most cases, something different happens because of the melting. So now I want to introduce you to Eldridge Moores, who he and I were roommates in grad school at Princeton, and he's a professor of geology at UC Davis. And so he was working with Hess just about the time Hess came up with this idea of the serpentine. And Eldridge thought it would be really interesting to see if you could find some old rocks at the surface. Not deep down under the ocean where you can't get at them, but at the surface, some old rocks that had been through this process. And he wanted to see if they were serpentine. So I want to now take you to Cyprus and show you what Eldridge discovered. Okay, so here's that map that some of you've had a chance to look at. The clickable map, and if you click on Cyprus over there on that island in the northeast corner of the Mediterranean, you'll find out all about it. And here's a satellite image of the island of Cyprus, and this thing is there. You see that dark thing? That's a mountain range that we're going to talk about. It's called the Troodos. This is Turkey up here, and here's Cyprus. and this is the Troodos Mountains. So that's where we are. This is Syria, Lebanon, Israel, Jordan down over there. So Greece is over here someplace. Okay, so now let's learn something about Cyprus because it's really important for our story. Here are the Troodos Mountains, seen in Cyprus. There they are off over there, and I had a chance to go there in, I think, about 1990 with Eldridge, and also with my wife Millie. I want you to meet her because she's going to be able to sit in the stand up, Millie. Just so. Especially if any of you are interested in mental health or psychology or social work, talk to Millie because that's her line of work, and she'd love to get to know you. Anyhow, Millie and Eldridge and I went to Cyprus in 1990, and it was kind of like a pilgrimage for me to go to the Troodos Mountains with Eldridge, because what he discovered there was so phenomenal and so important that it's like one of the great sites of geological knowledge. Okay, so we started climbing up into the Troodos Mountains, and we went through this pretty little village called Kakopetria, which Eldridge explained to us in Greek means evil rocks. And I thought, that's a good sign. Okay. So we climbed a little bit higher, and there was a sign leading to Kakopetria, or to the Troodos, and Eldridge had been telling us this great story about what he discovered there, and I was a little skeptical, and I was even more skeptical when I realized that in front of the signpost was a great big pile of horse manure. But we carried on up, and we started to come across things which were ancient ocean crusts, but they were not serpentine. They were not that green, shiny, blue-green stuff that you see in California. They were basalt, lava, old lava. How many of you have seen these things? These are called they're called columnar joints in basalt. Has any of you ever seen that? Okay, so this happens when the basalt flows out on the surface, and it's hot, and then as it cools, it shrinks, and the shrinking breaks it into these cracks. So this is absolutely typical of basalt. This is not serpentine. Basalt is a volcanic rock. So that means that this rock had been melted, and this is sort of the first chance I had to see in the field that rocks associated with seafloor spreading had actually melted. Wasn't just that they got wet and turned into serpentine. They actually melted. And then did I go backwards? No, what am I doing? I got confused here. Okay, I know what I'm going to do. Now I'm going to show you a map. That's what happens next. Okay, so remember here the Troodos Mountains, and those basalts that we were seeing were up in here someplace. And now I want to show you a map of what this looks like, a geological map, because these are the maps that we geologists make to help us understand what rocks are there and then what history the rocks are telling us about. So the next one is going to be in this. This is actually pointing north like that. So here is that area. And now the Troodos Mountains go from the edge of these bluish colors over to this edge of the bluish colors, and the high peak is right there. This is Mount Troodos. Now if you look at this with a geologist's eye, what you would think of is, why has it got this sort of a bullseye pattern here? It has that if you think, supposing that you had a bunch of layers of lasagna dough in a pan, right? And underneath it you had put a little inflatable cushion or something, right? So then you're pumping on it, and so right in the middle of the lasagna layers it starts growing this bulge like that. Okay? Then supposing you took a sharp knife and you went right across the top. Then in that bulge, where you'd taken the bulge off, you would see the oldest layers there, right? They would have been the ones that were at the bottom, and they've been bulged up and then cut off like that. This is a bulge right here. So right here you are seeing things which originally were much deeper. Now they've been pushed so high that they make the mountain, but this is a bulge that came up. And these are mantle rocks. These rocks were way down deep in the mantle, okay? Then think of it now, can I borrow this? Okay, now imagine here, okay, here's the bulge. The bulge happened right there, right? Where am I going to put it? Here, this will work better. Okay, now imagine that the whole thing was bowed like that, bowed up into an upfold, and then you sliced it across. Then you would see the oldest part down here, and these would be younger with the layers going down like that. So if you look at this with a geologist's eye, here you are seeing the deepest, oldest part now pushed up to the surface. And then this kind of stuff would be present but down underneath all over here, because here you're seeing shallower levels, and then finally they disappear out like this, and this is much younger sediment that doesn't have anything to do with old ocean crust. But this is old ocean crust, and you're seeing the whole sequence there from deep down in the mantle up to the basalts, which the columnar joint basalts, which are right at the surface, which are there. Okay? So they're basalt pillow lavas, and what I want to show you now is what's in this square. And I'm going to tell you now the story as Eldridge told it to me. And sometimes in your life, you might get involved with a discovery that is so amazing that it's just absolutely frizzles you up somehow. And when Eldridge told me this story on the phone, I was asking him one time, Eldridge, tell me that story so that I can tell it to one of my classes. And he started telling me this story, and at a certain point he said, Walter, as I remember it, right now the hair is standing up on the back of my neck. So this is a young guy who goes here because his thesis advisor, Harry Hess, has this ridiculous idea about seafloor spreading that nobody else thought made any sense at all. And so he's now talking about looking at the map that is inside that red box. And now we're going to see a detailed map. So this is the area inside the red box. Let me go back for a second. You see it's pink here and sort of blues and greens over in the upper right-hand corner. That's what's going on here. Here's the pinks, there's the blues and greens. So all of this stuff is not columnar basalt, but it's of basalt composition. It's basalt, but it's something different. So Eldridge told me about how one night at Princeton, he was in the geology library late at night, and he had found this map of Cyprus from a number of years before seafloor spreading. So it was made by a guy who wasn't thinking about seafloor spreading because it hadn't been invented. Made this map, and Eldridge is looking at it, and just trying to figure out what it all means, and he sees these little symbols here. And this symbol is made like this. It's that's the wrong one, whiteboard there. It looks like this. And then it's got a bar and it's got a number like 30. That's a geologist's symbol for the orientation of beds in sediments. This? So imagine now we're looking down on the surface of the land. This means that these beds are tilted like that, 30 degrees down. That's what it means. It means beds, right? Sedimentary beds. Eldridge is looking at this for a while, and then suddenly he has this sort of something intrudes it's upon his mind, and he says, wait a minute. Sedimentary beds, this isn't sedimentary beds. These are basalts. These are volcanic rocks. They don't have beds in them. What are those things? Why has he got beds in a volcanic rock? What do you do then, of course? You look at the legend on the map, right? So Eldridge looks at the legend, and here's the legend. And it shows those symbols, and it says strike and dip of multiple dikes or sheeted structures. Now what could that be? And Eldridge had never heard of multiple dikes, but he did know about sheeted structures, but he did know about dikes. So here's what a dike looks like to a geologist. I took this in Yosemite one time. It's a piece of granite, and you see that white band going through it? That's a place where the granite, which was cold, cracked and just split apart and made a little crack, which as you can see is maybe about an inch wide. And then some molten rock came up and filled it in. So that white is a younger filling. It was molten at a time when the granite was no longer molten, and it filled it in. So look, what does this thing mean? This means that there has been extension here about an inch. These two sides used to be an inch closer together. Now they've spread apart. And in the space that opened up, there came in molten rock that filled it in. That's what a dike is, okay? Sorry, you might be amused that if this is a dike, the geologists call this the country rock. which is not a musical style, but it's what was there before the crack took place. Okay, so that's a dike. So what's a multiple dike? So Eldridge then, looking through this 1959 mapping study of Cyprus, sees that there are things called sheeted dikes. And as he reads through this thing, and now the hair's really standing up on the back of his neck, he realizes that sheeted dikes is just one dike after another, after another, after another. So if this is a dike here, and this is the country rock is a dike that was there before. And that dike filled in when this dike broke apart. So what does that mean? It means that this whole outcrop here didn't exist at all. It was here and it has gradually spread out to that width. Spread. It's spread, as in seafloor spreading. And as here's Eldridge, this young guy sitting in this geology library late at night, when seafloor spreading is just a wild idea, and suddenly he realizes this could be the evidence for seafloor spreading. Maybe the whole of Cyprus was entirely spread like that. Yes. Is Alex?
Yes.
Yeah. Alex?
Is that a bird's eye view picture?
No, I'm sorry. This is an outcrop. The hammer, I'm sure he's got the hammer stuck on a little ledge. That's a good question, right? No, you're just standing here looking at the side of a quarry or something like that. So here, sheeted dikes was the first indication that you could have had spreading that was so enormous that you could form a whole ocean that way. What a cool discovery. Can you imagine making that discovery, especially as a very young scientist? So here is the thing now. That whole pink area was never even there until the seafloor began to spread and spread out so wide that it filled that entire area in one dike after another. Okay? All right, so Millie and I got to go there with Eldridge, and we got to see things like this. This is an amazing outcrop. This is Eldridge on it. And this is a set of dikes here. And then in between are pillow lavas, which are what forms when basalt pours out on the seafloor. Under all of that water, it forms these sort of lumpy things. And here's some more dikes over here. This is the evidence. This is the direct evidence that seafloor spreading was not just a goofy idea. It was right. And then after the seafloor had formed, then sediments were deposited on it. These white rocks here are sediments that were deposited on top of the seafloor that's represented by the whole Troodos complex. Okay, so now you've had some geology background. Now it's time to go back to the Bronze Age. You ready? Another breathtaking jump. Okay, let's go. Okay, so now let's learn about bronze. I've been passing that around and you've been looking at that little statue. So bronze is an alloy of copper and tin. And brass you might also know about. It's an alloy of copper and zinc. Copper is a soft metal. Tin is a really soft metal. And oddly enough, if you mix them together into an alloy, it becomes very hard. Again, if anybody wants to know later, I'll explain why that is. But this bronze was the first metal that humans started working that they could easily work and which would become very hard when it was done. So you could make all sorts of useful tools and weapons and things out of it, like that of it. So that's bronze. And what we're going to talk about mostly from here on is where did the copper come from, and then we'll talk a little bit about where did the tin come from. Okay? So let's go on. Here's some bronze artifacts from the Cyprus Museum, which is just amazing. Cyprus is just maybe the richest Bronze Age place that there is in the Mediterranean. And the archaeologists have uncovered all of these incredible artifacts, which of course lay buried after the catastrophe of 1200 BC. They just lay there buried until maybe the 19th century or the 20th century when archaeologists dug them up. So they have these wonderful things there. Okay, here's a map now of of Europe and the Mediterranean and Western Asia. in about 1850 BC. So we're not in the late Bronze Age, we're even in the early Bronze Age here. And there is a mark on here, which I've now marked in red, that says limit of bronze working. So all of that area inside that looping line was where people were at this time able to use bronze to work on it. In the area to the west, like Italy and Spain and France and England and Scandinavia and Germany, they had not yet learned bronze working technology. They were still in the Stone Age in that area, maybe the Copper Age. But bronze was that sort of Middle East, Western Asia. That's where it was. Now let me show you something interesting. There's Cyprus. It's kind of right in the middle of that. It's almost like in the focus point of that loop. Huh? Okay, so let's see whether that's just coincidence or whether it means something. But first of all, let's think about bronze for a second. Now, bronze, it was a great, great invention. I mean, imagine once you had bronze and a nice sharp bronze sword, you no longer had to beat Alex over the head with a rock. You could just stab him. It was much more efficient. So it was a great step forward in the progress of civilization, right? Unless he happened to have one too. Okay? And so helmets and swords were made out of bronze. It's nearly as hard as iron. And then the thing on the right, anybody recognize what that is? What does that look like? Looks like a sheepskin to you? Remember there was Jason the Argonaut and Jason, yes?
It's a shield.
It's actually not a shield, it's an ingot of copper. And they, for some reason, like to cast them in the form of a sheepskin because sheepskin was what Jason and early gold miners used in order to capture the gold. You know, if you have gold like in the streams in the Sierra, when that flows down, the gold is the heaviest stuff, so it would get caught in a sheepskin if you laid a sheepskin on the bottom of the stream. And then after a while you take the sheepskin out and you burn it and the gold falls out. So sheepskins were somehow closely associated with ancient metallurgy. And so for some reason they like to cast these copper ingots in the form of sheep pelts, you know, with a sheep fur on it, fur wool on it, right? Okay, so this is sort of stuff that's in the Cyprus Museum. Okay, so here now is our map again of the Troodos. And remember how this works, that we can think of this as a sort of a big folded sheet of paper here, right? So that here it's cut off and you're seeing the deeper parts. Here the very deepest because it's bowed up. And as you go in this direction, the layers kind of disappear under like that. So when they go under these younger sediments, this edge here is the very uppermost part of the old ocean crust that this represents. That makes sense to you guys? Anytime you want to ask a clarifying question, please do. Okay, so on both sides, here and here, this was the very shallowest part of the old ocean crust, what was right in contact with the seawater. Okay, so right here is a place called Skouryotissa. And Skouryotissa is an ancient copper mine because it turns out that it's not a coincidence that Cyprus was right in the sort of focus of that zone of bronze working. It was there because Cyprus was the greatest center of copper production in the ancient world. Anybody here from Los Angeles area and know Harvey Mudd College? Anybody know about Harvey Mudd College? Okay. Harvey Mudd College is named after the son of a man named Seeley Mudd. And Seeley Mudd was an American mining engineer and geologist back around the turn of the previous century. And at that time, this is a little bit of a digression, but at that time, say about 100 years ago, electrical wiring was coming into use, and there was need for copper, and copper previously had not been a very important metal, but they needed sources of copper. So guys like Seeley Mudd went out looking for copper. And anybody here from classics? Okay, well, Seeley Mudd had the advantage of having studied classical languages. And it occurred to him one day that the word Cyprus might be related to copper. And so he thought, well, what the heck? So he went to Cyprus. It was not a copper producer or anything. And he started poking around, and he started discovering these ancient Bronze Age copper mines all over Cyprus. And Skouryotissa is one of those. It was a copper mine in antiquity, and then after Seeley Mudd, it became a modern era copper mine. It was reopened after maybe 2,000 or 3,000 years of having been forgotten about. So Skouryotissa, here is what it looks like, or what it looked like when we were there in 1990. It had been very active until the Turks invaded Cyprus in 1974, and the dividing line between Turkish Cyprus and Greek Cyprus was very close to Skouryotissa, so the Turks could have shelled this anytime they wanted to, so it stopped being inactive. You couldn't work it anymore, it just was too dangerous. And so it just sat there, and as it was, and we had a chance to go with Eldridge and with a man named George Constantinou, who was a Cypriot geologist from Cyprus. And so this is a great open pit mine of Skouryotissa, which was worked until 1974 and then abandoned. You can see these sort of, the horizontal layers on there are the remains of what the terraces were where the mining trucks would drive along. They were basically hauling the whole thing away, all of this material, to get the copper out. Well, in the Bronze Age, they weren't nearly as efficient, so they had to go for the high-grade seams of copper that were in there. Not the whole thing like they're mining now, but just the rich ore. And so these things right here, can you see those sort of dark things? Those are places where the modern excavation intersected old underground tunnels that dated from the Bronze Age, that dated from maybe 1500 BC, in which miners were going down there following these veins of rich copper and bringing it out. So I thought this was absolutely fascinating to see this. And so we got to poke all around there. And here's Millie. And this is an example of what are called ochres. Is anybody here an artist and ever used ochre? Okay, ochre is a pigment. It's a kind of a yellowish pigment that artists use in their paint. And this is the original source of ochre. All right? And ochre is rich in copper. So here just show you the copper contents. These are the sediments. They don't have very much copper in them, 0.1%. Then there's a real rich ore here, which is 2% copper. That's what those guys were following underground in the Bronze Age. And then there's the ochres, which are slightly altered. They have a little over 1% of copper in them, and that's what's being mined now. Okay, so this was the source of Bronze Age copper. And there's a couple of interesting things about this. So here's Eldridge with his back to us, and then George Constantinou did he's a geologist from Cyprus who did his PhD with Eldridge at Davis, and then when we were there, he was director of the Cyprus Geological Survey, so we went out there together. And George has been really interested in trying to understand this ancient Bronze Age copper industry. Right? So here's one of the things that they did. They're looking at an ancient slag heap. What's slag? Well, if you mine that ore, then you have to heat it up. You have to have a real hot fire. You heat up the ore, and the copper kind of comes running off as liquid metal, bright incandescent red. And what's left is slag. In other words, it's the ore that has had the copper removed. And George has done a lot of analysis of these things. So this pile was built up probably over hundreds of years in the Bronze Age as the miners were working through this. And what they found was that clearly copper refining techniques had improved as the Bronze Age went on. And here's how you can tell. If you look down at the bottom, the lower part of the pile, there's more copper left in the slag. And if you go up higher in the pile, there's less copper left. So what that tells you is that as this pile grew over the years and the decades and the centuries, they got better at extracting the copper because there's not as much left in the stuff at the top. So this, think about it now as a big historian. This is a way of learning about history, in this case the history of Bronze Age mining, and you do it with archaeology and chemistry. That's how you're learning it. So we're going to look at all sorts of different ways of finding out different kinds of history in this class. So anyway, they were getting better at extracting the copper because they could heat it hotter and hotter, partly because of the way they built their furnaces and partly from making better charcoal and hotter fires. But the key thing is that in order to get the copper out, you have to have a hot fire. Clearly they were using charcoal. Now, I'll take you for a moment to Italy. This is charcoal making. This is how, I don't know, I'm sure you've all seen charcoal or cooked with it. Maybe you haven't seen it made. This is how charcoal is made. They cut all of these dry oak sticks, and then they make this sort of an interesting dome-shaped mound. And then they cover it over with dirt to keep most of the air out, and then they set fire to it. So there's one of those piles under here. It's covered with dirt, and down here in the bottom, maybe you can see there's a little steam coming out of some holes. Basically, they burn it with just barely enough air in it to burn, and what that does is that drives off the water that's in the wood and leaves the carbon behind unburned. So charcoal is the carbon that's left after you've driven the water off of this wood. So they must have been, you can make a much hotter fire with charcoal than plain wood. So in Cyprus they must have been getting better at making charcoal. But there's a problem. So what George Constantino had calculated was, he calculated how much copper was extracted from Cyprus in the Bronze Age, and you could do this basically by just figuring out the volume of that pile of slag, and you say, well, how much did they get out of it? You get a rough idea of how much copper. And there was enough copper taken out of there, clearly, to supply all of the Bronze Age in all of the Middle East and Turkey and Greece, right? But the problem was that in order to extract that copper, you would need a lot of charcoal. And George calculated it, and it turned out you would need a forest 17 times the size of the whole island of Cyprus. How could you do that? Bring in the charcoal from somewhere else? That's an awful lot of charcoal to bring in. Well, it turns out that Cyprus, with Mount Troodos is high enough that clouds gather there and it rains. And this is the Eastern Mediterranean. Think Israel. It's very hot, very dry. Cyprus has this high mountain, so the clouds gather there. It rains. You get enough rain on Cyprus to keep regrowing the forests. So the 17 times the area of the island just means that they were doing this for a long, long time so that the forests kept regrowing. And then they make charcoal, and then more forest would grow, and they'd cut it down and make more charcoal. And Cyprus is really the only place in the Mediterranean that had this possibility. There are lots of other places in the Mediterranean that had copper. For example, Lebanon had copper ore. But Lebanon was so dry that once the forests that were there had been cut down and turned into charcoal, no more forests would grow. There was a lot of deforestation took place in the Bronze Age. Only in Cyprus did the forests keep regrowing so that you could get enough charcoal to keep extracting copper. And this was the key metal, right? Copper plus tin makes bronze. This was the heart and soul of the Bronze Age. George told us about a letter that has been discovered, inscribed in, I don't know, probably pottery or something like that. It was a letter from the Pharaoh of Egypt to the king of Cyprus, basically saying, "Dear king, please send us more copper. We'll send you as much gold as you want. Just send us copper." You had to have that because that's what it took to make the tools and instruments that were important at that time. Okay? So rainfall in the high Troodos Mountains makes firewood a renewable resource on Cyprus. So, conclusion, most of the copper for the Bronze Age came from Cyprus. Okay, now, at this point, don't talk to anybody, just take a moment and take a breath and relax and get your attention refocused, and we're going to get the rest of the story in a moment. Pardon? Yeah. Come back right away. Yeah.
How deep are the tunnels?
How deep are the tunnels?
Yeah.
Well, it looks like they were probably many tens of feet below the ground at the time. Yeah.
Like, they weren't scared that it would like collapse.
Well, they miners know how to shore up the tunnels with timbers, so they don't. But they were really small, so often it was the children were forced to work in them. Okay, folks, you ready to go? Have you finished getting your attention back? Let's see how the last things come together. So I want to take you back in another breathtaking jump. I want to take you back to exploring the mid-ocean ridges. Okay? So here is a mid-ocean ridge, and schematically shown, think of it, here's deep mantle coming from the deep earth. It turns here, it spreads like that. Right here it melts. And then the melt crystallizes to form basalt. So a good way to think about the mid-ocean ridge is that it's a chemical processing plant. And the input, the raw material, is deep mantle rock. And right here, all of the action takes place. This is the factory. And then it rolls out this continuous strip of ocean crust. So let's see a little bit what happens there. So this man, Morris Ewing, I worked for him as a postdoc at Columbia University, and his ship there, the Vima, all full of oceanographers, had explored the world oceans just in time to supply the information that made the plate tectonic revolution happen. But here's what the oceans of the world look like at the present time, and you can see here, I'm going to cover them up in the middle, but see the mid-ocean ridge coming down there? And the mid-ocean ridge is where the seafloor is taking place. And so it bounds different plates, but people realized that it would be really interesting to go down and look at those mid-ocean ridges. We're now talking about 1970 or something like that. Now, you cannot go in the Alban or any submersible down to these parts of the ocean. They're so deep that it would just crush the submersible. But you could, and it was possible, to go just deep enough to get to look at the mid-ocean ridge. People started doing that, especially people like Tanya Atwater, who's a professor at UC Santa Barbara. So they went down on some of these places, and you see that one in the Atlantic there? What did they find when they went down with the submersible? Well, here, this is kind of the lighting's kind of harsh because we're so deep that there's zero light, zero sunlight here. This is absolutely pitch black, so it's being illuminated by a searchlight on the Alvan. But what you can see here is a kind of a crack. Imagine what happens if you have seafloor spreading taking place and you pull it apart. It's going to make a crack, right? That's the crack, right there. That's where seafloor spreading is taking place, right exactly at the axis of the mid-Atlantic ridge. And sometimes it's just a crack like that, but sometimes the crack went deep enough to get down to that melted rock, and sometimes the melt would come pouring up. So this is another picture, and these strange looking things, that's what basalt magma does when it pours out under the water. And I could tell you later about it, but these are called pillow basalts, and they're what happens when basaltic lava flows out in the water, or under the water in this case. So here you had evidence. At the place where the seafloor spreading is taking place, you get fracturing, and sometimes the fractures let melt come up to the surface. Okay, and sometimes, and we'll see in a moment why this works, you find these things, these chimneys. Do you see this chimney here with stuff pouring out of it? This thing is just a part of the instrument panel on the on Alvan. But this thing is called a black smoker, and I have a picture here of a black smoker, and this is a ratty video, but let me show you so that you can see what this looks like. This is very, very hot water just rushing out of here, and it's kind of black because it has a lot of metal and stuff in solution there. And so, oh, I'm sorry, I meant to show you here. So that's what these things look like. And these are going on the floor of the Mid-Atlantic Ridge and all the other mid-ocean ridges. Some of you have probably seen these before. I don't know. Have you seen these on Discovery Channel or something like that? Anybody seen these? Uh-huh.
What is the environmental water temperature?
I don't know the actual temperature here, but a friend of Millie's and mine named Roger Larson was on Alvin in one of these early dives, and they wanted to find that out. So they made a temperature probe on the end of a rod sticking out from the Alvin, and they got up there and they put it right in there. It melted the temperature thing, so hot, really hot. I don't know the numbers, but that's a practical definition of hot, right? Okay, and then you probably know about these things. They started discovering around some of these black smokers these incredible colonies of animals that nobody had ever heard of before. These things are called tube worms. And you might be able to see if here there's a little crab walking down around there. These were so weird that when they brought these things back and sent them to the Smithsonian, the biologists there didn't even know what phylum to put them in. They were really, really strange. So nobody had ever imagined that down on the crest of the mid-ocean ridge, you would have life in forms that nobody ever thought of before. There's no sunlight there. These things are working on some sort of a chemosynthetic food chain. It isn't a photosynthesis-based food chain. And they discovered all these amazing things. Bacteria on which the tube worms live may be of great significance in life history. And maybe life got started at deep sea vents, protected from frequent big impacts on the early Earth. So these things may have something to do with the very early history of life. Okay, and they just found all these things, like here, for example, is a crab walking around down in the bottom. Nobody expected to find these things. In fact, what they said, the first time they found a crab, they were in the Alban and they were going along, somebody said, hey, look, there's a crab. A crab. A crab. A crab! What is a crab doing on the bottom of the ocean? So then what they did was what any scientist would do. They poked around and they found out where there were more crabs and where there were fewer. And as Roger said, they drove up the crab gradient and they came to a black smoker. And that's where the source of all of this is taking place. Okay, you may be thinking that this is just another interesting picture from the bottom of the ocean. But in fact, this is the most important picture in the entire talk today. Can anybody see why? Yeah. Ochre, bravo. What's your name?
O'Share?
O'Share. Thank you very much. Yes, it's the color. These things are crawling around on the modern seafloor on ochres, just like Millie was standing on here in Cyprus. And so the whole point here, the point of all of this stuff, is that Cyprus was the source of the copper that made the Bronze Age possible. And that copper formed in ancient black smokers on the floor of some ancient ocean as it was spreading. There must have been chimneys here. There must have been tube worms, there must have been crabs crawling all around. That was the environment of the Skouroiotis copper mine about 100 million years ago. So here's what was going on. There was what we call a hydrothermal cell circulating here. Remember, this is now pulling apart. This is the mid-ocean ridge. Seafloor spreading is taking, so it's cracking here, right? And as it cracks, there's all of this cold, deep water on the ocean floor that's under huge pressure because it's got 2,500 meters of water above it. It's driven down into these cracks as they form. And as it's driven down, it gets closer and closer to this melt where these rocks are really hot. And that heats it up. And of course, when water gets hot, it tends to rise. So it comes rising back up here. But meanwhile, you've had this hot ocean water, which is a really powerful solvent. It's been in contact with these deep rocks, and it's leaching metals, copper, iron, zinc, sulfur are leached from the basalt by the hot water. They come up to the surface right here, and right here is where the chimneys are. And right at the chimney, you have this hot water all rich in dissolved metals. It comes in contact with cold water. What does that do? It precipitates out those metals. And so those chimneys, if you take a chimney apart, the chimney is really rich in copper and all of these other metals. And then eventually the chimneys kind of fall apart and they spread all of this out there. So that's where that copper comes from. That's happening now. Say, for example, here on the crest of the Mid-Atlantic Ridge. This is a Russian study. And here the scale 250 meters. So this object here is kind of the size of Memorial Stadium, right? And as you look at that, they map this thing very carefully in detail. There are black smokers, and there are also another kind, white smokers. And then there are extinct smokers that used to be active, and now the hydrothermal system is jammed up so that the chimney doesn't work anymore. And when the chimneys stop working, they eventually sort of fall apart, and they spread all this metal-rich sediment around. And sometimes some of it is enriched in massive metal ore. So this place that the Russians studied in the middle of the Atlantic Ocean on the mid-ocean ridge probably looks just like Skouryotissa did 100 million years ago. And that's where the copper came from that made the Middle Eastern Bronze Age possible. And it turns out that none of those animals fossilized very easily, and so there was a long, difficult search. And finally here, from Cyprus, from those copper ore things, they found a few little snail shells, and the tracks, see, here's a modern tube worm, and this is an ancient tube worm cast. So it's quite clear that there were these living vent colonies also on the floor of the ocean there where Skouryotissa is now. So here's our conclusion. The Cyprus copper ores that made the Bronze Age possible were formed at hydrothermal vents on an ancient mid-ocean ridge. I'm not going to go very far into this. In fact, I'm only one slide, but there's another whole thing, and that's where did the copper come from in the first place? If you know anything at all about the Big Bang, you know that when the universe formed, at the end of the Big Bang time, there were only two elements. There was hydrogen and there was helium. There's a tiny bit of lithium, but basically it was all hydrogen and helium. There was no copper. How come there's any copper at all on the Earth? And we'll get into that next week. But the answer is that innumerable supernovas produced copper and tin. They produced these elements heavier than helium. They were formed partly by nuclear fusion and then partly by the collapse that leads to a supernova. And then when a supernova collapses, it sort of bounces, and part of it goes spreading out into a vast explosion that spreads whatever was in that star all over that part of the galaxy. So copper was made in stars as they collapsed, and then the collapse blew some of that stuff out into the galaxy, and it became later incorporated in solar systems like ours and planets like the Earth. So there's not only the story of where did the copper come from that's in Cyprus, but where did the copper itself come from in the first place? So see, what I'm trying to do here is tie together all of these parts of big history. So there's Earth history on Cyprus, there's cosmic history and supernovas, there's life history with those hydrothermal vent colonies, which may have been the original oases where life was formed. And finally, let me take the last few minutes we have left and say, where did the tin come from? Because bronze is an alloy of copper and tin. And where did the tin come from? Because tin doesn't form at mid-ocean ridges. And no tin is mined in Cyprus. Where did it come from? Well, here's what I'd always heard. was that it came from Cornwall, which is in southwestern England. Cornwall is a great tin mining area, or it was until the mines were all worked out. But this was the main source of tin in the modern era, was in Cornwall. And so when you read about the Bronze Age, you would always read, yeah, and they brought the tin back from Cornwall. Cyprus produced the copper. And I always thought this kind of seemed a little bit unlikely. You remember the other Homer story? There's the Trojan War story. You remember the other story is the Odyssey. Remember Odysseus was a guy who'd been in the Trojan War, and he was trying to get back from Troy, which is near modern Istanbul, to Ithaca, which is in Greece, you know. You drive there in a day now, right? And it took him 20 years to get back because he kept running into all these awful navigational hazards in the Mediterranean, like sirens and like Cyclops with one eye who wanted to eat him up, right? So basically what that's telling you is that in Bronze Age time, sailing around even the Mediterranean wasn't all that easy. And then if you had left the Mediterranean through the Straits of Gibraltar and started up here, this is some of the worst water in the entire world, the Bay of Biscay here. Now, would this be, it just never quite sounded right to me. Was not in a position, yeah, you?
Did they even have sailboats anyway?
I think they did, but they also did an awful lot of oar propelled. Yeah, there were galleys with, but either way, it doesn't seem like you could have brought enough enough tin from Cornwall to make all that bronze with that vast amount of copper that was coming out of Cyprus. Yes?
How do we know that the bronze was made in Cyprus, even though Cyprus is the main source of copper?
That's a good question. Well, could the bronze have been made somewhere else? Sure, it could have been, but you probably don't want to carry that stuff too far. Probably copper would have been a commodity that was traded, and there would have been bronze smiths elsewhere. But I think the real problem is, how do you get the tin? Can you really get it from Cornwall? Well, it turns out that Cornwall is not the site. If this problem was solved a few years ago, it came from Turkey. Right across the strait, you can see Turkey from Cyprus and vice versa. And nobody knew that there was tin in Turkey until quite recently. It was discovered by a Turkish professor, I don't know how you pronounce her name, maybe somebody does, at the University of Chicago. But she was doing archaeological work on Bronze Age sites from this part of Turkey, and at this place called Goltepe, she was able to identify that this had been a Bronze Age tin mining site. And so there were things like, here was a crucible in which they would grind up the ore before they put it into the fire to get the tin out. And she got a lot of flack about this early on. People said, there isn't any tin there. Analyze it, and you see there's no tin there. And she said, well, of course, they extracted it. That's what they were doing. But there was enough around to make it clear that this had been the source of tin. So this was a kind of a nice little nexus there. You had the tin in Turkey, the copper in Cyprus, and they form in completely different geological environments that happen to have been brought together by plate tectonics. Cyprus and Turkey didn't used to be next to each other, but kind old plate tectonics put them next to each other, and that made it possible to make this the center for the Bronze Age. So here again is our map, and there are the sources of copper in Cyprus and of tin in Turkey, and right at the focus of that area in which bronze working was going on. So final summary, where did the metal come from that made the Bronze Age possible? The copper came from Cyprus, from ancient hydrothermal vents on the ocean floor, mineable because Troodos Mountains kept Cyprus wet and forested. Tin was in Turkey, coming from ancient granites. And that was what made all of this possible. So behind a great legendary story like the Trojan War lies an intricate and fascinating texture of cosmic history, earth history, life history, and human history. That's what our course is about. And here's a final thought. I have just time for this. The mystery of the end Bronze Age catastrophe is comparable with the mystery of dinosaur extinction. In each case, each one was followed by a dark age and then by a recovery. So that's something to think about while you're reading T-Rex and the Crater of Doom. And you might say that classical Greeks marks the recovery from the Dark Age, just as we mammals represent the recovery from the extinction that removed the dinosaurs. So that's my story, and just let me remind you, everybody meets here at 5 o'clock tomorrow afternoon, and we'll do all the logistical stuff